We're starting with Chapter 3 of Quantitative Chemical Analysis to give us some tools for dealing with experimental error. So Chapter 3 contains several different topics. Section 3.1 is a review of significant digits, and I am going to skip over that here because I've already done a video in the review section for significant digits with some examples on how to do calculations. So I'm going to go ahead and let you work on that part separately. So instead, I'm just going to jump ahead and start with section 3.3, which looks at types of error in measurement. So we have two main types of error that we're going to talk about. We're going to talk about systematic error, and that's where we're going to start here. And systematic error is error that occurs if we have a problem with our equipment or with our experimental design. So a problem with our equipment, you could imagine, for example, if I have a graduated cylinder and I get this graduated cylinder out of the stockroom area, and I don't notice that there happens to be some little grunge or something that's stuck in the bottom here. And so when I am using this graduated cylinder and I'm pouring out my desired quantity of a liquid, then every single time that I use this particular dirty graduated cylinder, it's going to deliver a little bit less liquid than I'm intending to deliver because it's got this little stuck-on grunge that's taking up some of the space. So it's going to deliver a volume that is consistently too high or too low, depending on the error. In this case, it would be consistently too low or lower than what we are intending. So it's systematic because it's the same every time. So this is one of the things that we want to pay attention to about systematic error, that this is one of our important parts. The error is the same every time, and the error can be corrected. So with this dirty graduated cylinder, the only thing I would need to do would just be to clean out that gunk that was in my graduated cylinder, and then my volume would be back to what it was supposed to be. I would just be delivering my, whatever the desired value was. It wouldn't be short. So another problem with equipment or experimental design that you might imagine is if we have something like some kind of glassware or probe or a balance that is either uncalibrated or like with a balance, it might not be taired. So it might not be showing a 0 if it is an electronic balance, for example. And this could lead to measurements that are either too high or too low. So you could have a positive or you could have a negative error. And this is a third part that we need to remember about systematic error. So the first one is that our error is going to be the same every time we do a measurement, and it can be corrected by fixing whatever the problem is, and that we can either have errors that are always too high or always too low, but it's always going to be the same. The only real way that we can figure out whether or not we have systematic error taking place in the first place is that we must compare our measurements to a known value. So in the case of a balance, I might take a standard weight and put it on the balance, and then I could discover, oh gosh, this is supposed to be a 50-gram weight, and it's really reading 52.315 grams, and then I might actually notice that I hadn't tiered it. So this is basically the only way for us to figure out whether our measurement is sort of real or whether we have some kind of a systematic error going on. So it can be a really subtle error to discover, and it's one where we need to really be careful about our experimental design and make sure all our glassware is clear and be really meticulous about taking data in the lab. Our second type of uncertainty in measurement is called random error. And random error, as you could maybe guess from the name, is random. It is in all measurements, no matter how careful we happen to be. And our fundamental pieces of random error here are that each measurement will have some positive or negative deviation from the actual value. And we can't predict whether it's going to be positive or negative. And the second part we need to remember about random error is that it can't be corrected. Every measurement, no matter how careful we are, is going to have some amount of random error in it. And the random error is intrinsic to the measurement technique. So the amount of random error will depend on whatever our measuring instrument is. So let's look at a couple of examples. A simple example of a measuring instrument is a ruler. So I went ahead and took a picture of one of my pens lined up with the ruler. It's a little hard to read all of the gradations, so I took a video as well. So I lined it up with 0, and now as we're looking, these are centimeters. So you can see that the total length of this pen is about 14.1 centimeters. Is it exactly 14.1 centimeters? A little more? A little less? Well, I have to make a judgment call, and as soon as I do, I've introduced some random error. Next time if I'm measuring it, I might make a slightly different decision, or if I had a bunch of different people measuring it, they all might think it was a little bit different length too. Okay, let's shift back to my notes. If we look at glassware as another example, glassware comes with a published tolerance. And if you look at Chapter 2 of Harris's Quantitative Chemical Analysis, there's lots of information about different kinds of glassware, and I encourage you to take a look at that, especially as you are doing our lab this week. So if we look at some glassware, let's look at a couple of analytical glassware. So if, for example, we are looking at I have to also talk about the class. The Class A 50 milliliter volumetric burette. All burettes are volumetric, I guess, so that's redundant. So if I think about this Class A volumetric burette, it has a published tolerance of 0.05 milliliters. So this tells you that when you are delivering some whatever solution it is that you're using with your burette, each of your measurements should be within plus or minus 0.05 milliliters of the actual volume that you intend to deliver. If you look at a Class A 10 milliliter volumetric flask, volumetric flasks we will be using in our first lab for sure. It's a little flask that looks like this. It's got a little line right here, which is the fill line, And volumetric flasks are rated as TC, which means to contain. That means they're supposed to contain the amount of liquid intended. In this case, a 10 milliliter volumetric flask, you would need to fill the volumetric flask up to this fill line where the meniscus is just touching the fill line, and then it should contain 10 milliliters, and the tolerance is plus or minus 0.02 milliliters. So different glassware and different sizes of glassware are going to have different tolerances. And when we start talking about these tolerances and the size of the uncertainty, we also need to talk about the absolute uncertainty. The absolute uncertainty is exactly what it sounds like. So, for example, when I measured the ruler to measure my pen, I think when I'm looking at that ruler that I should be able to estimate to about 0.5 millimeter with this ruler. And so I said that I thought that my pen was probably 14.1 centimeters, and there's 10 millimeters, or excuse me, 10 millimeters in a centimeter. And so that would make my pen 14.1 centimeter plus or minus 0.05 centimeters for some absolute uncertainty. So rather than just talking about the absolute uncertainty, how big that actual uncertainty is, it's sometimes better to talk about the relative uncertainty. How big is the uncertainty compared to our measurement? And sometimes we also calculate the percent relative uncertainty as well. And you can imagine that's just the relative uncertainty times 100%. So let's look at this pen. If I have an absolute uncertainty of 0.05 centimeters, then my relative uncertainty is going to be the size of the uncertainty divided by the size of the measurement. So if I do this calculation, then I get 0.003, and there I'm going to do a subscript 5 for that next digit to indicate I have more digits later, but they're not certain. So if I multiply this by 100% to get the percent relative uncertainty, then I have a percent relative uncertainty of 0.35%. Percents are useful for us because we're kind of used to thinking about them. I might not know what to do with 0.0035. Looks like kind of a small number. And I think it maybe is a little bit easier for us to think about the size of numbers when we look at percentages. So 0.35% is quite a small number. That seems like a pretty good absolute uncertainty. So let's think about using this same measurement. Let's imagine that instead of my pen, which was 14.1 centimeters, I wanted to measure a Lego piece. It's about 7.5 millimeters wide. So I'm using the same ruler I did before. I estimated that the uncertainty was 0.05 centimeters. I guess I don't actually need centimeters. I can use millimeters here since I just said millimeters. So 0.5 millimeters is my absolute uncertainty. And if my Lego piece is 7.5 millimeters, then my percent relative uncertainty for this Lego piece width is now 6.7%, which sounds like it's quite a bit higher. Now I used the same exact measurement technique. I used a ruler, but because my measurement itself was quite a bit smaller, that uncertainty makes a much bigger impact on my percent uncertainty. So it's important to know, am I using the right tool? In this case, if I want to know how wide a Lego piece is, this probably is not the right tool. I mean, rulers are not terribly analytical, right? They aren't expected to be super precise. So I'd probably want to use a caliper or something like that. And there's vernier calipers out there that are good at measuring small widths to a much higher accuracy. So this is a good time for me to actually talk about those two terms I just used. And they kind of slid in here. I talked about accuracy, and I just talked about precision. So let's go ahead and review those two terms as well. So if a number is accurate, that means that our measurement is the same as the true measurement. So how would we know whether or not we had measured the true value? This is actually a really complicated question. And usually, if we want to know whether or not our measurement is measuring the true value, we need to compare our measurement to a standard material. And the standard materials are usually called standard reference materials. And they're often abbreviated SRM. And standard reference materials in the US anyway are created and maintained by the National Institutes of Standards and Technology. It's a governmental agency, and they produce a bunch of different standards for all different kinds of analytical applications. So these standard materials have been analyzed in a lot of different ways, and then depending on what your technique is that you're using, you would compare to that standard reference material. So you might measure the standard reference material and show that your measurement technique was able to accurately show the real value of that standard reference material. So then, if my balance, for example, if my mass balance is analyzing a 25-gram standard reference material, and it shows, it would probably have more zeros there. And if my tolerance for that instrument was 0.01 gram, and if my balance showed that my mass was 25.01 grams for the standard reference material for one measurement, and then maybe it was 25.00, and it kind of went back and forth within plus or minus 0.01 gram, I would know that my balance was giving me the accurate value for that standard reference material. And now when I measure some other sample, some unknown sample, and it says that it's 8.72 grams, I know that this is probably the accurate measurement within plus or minus 0.01 gram. So that's what accuracy is. Precision is whether or not we get the same answer within tolerance, the same measurement every single time. It could be the wrong measurement and still be precise within tolerance. So we've gone through a bunch of definitions. These are all in section 3.3. And now is a good time for you to do assignment number 1, which is some practice problems. And these problems are out of chapter 3 in the quantitative chemical analysis book. I'd like you to do problems 3.5, 3.12, 3.13, and 3.14. Some of these are pretty fast. They shouldn't take you too long. There's a lot of extra practice problems that I'm not assigning. This is just sort of like one of each. If you find that there are other problems that you, or any of the problems that you're struggling with, make sure to make a note of that and ask questions, or to do extra practice problems. There's also a lot of sample problems in this book. So use your resources and come and talk to me if you have any trouble.